Alright, for this video I just want to look at one simple problem, and that is given a two-component ionic ceramic, or mostly ionic ceramic. Remember, the ceramics have ionic and covalent bonds, and so there's some ionic character to them. If we're given the charge of the ions and the size of the ions, can we determine the crystal structure? Alright, so to answer that question, the first thing we want to do is take a look at the coordination number for different types of arrangements of the cations and anions in a ceramic structure. Okay, so the one thing we know is that the structure in ceramics has to be electrically neutral. Okay, so you'll see that theme coming up over and over again, especially when you talk about defects. So we need an electrically neutral ceramic, and so we have to make sure, knowing the charges on the ions, that we have the right ratio of cations and anions, and so we'll look at that in a second. And the next thing we want to do is we want to say, as a principle, that we want to maximize the neighbors of opposite charge. And so if I have a cation sitting here in the center of a certain size, I want to see how many anions I can fit around that particular cation, such that they're all touching the cation, and we can allow them to just touch each other, but we can't have the situation where they touch each other but they don't touch this particular cation. Okay, so that's going to set up different types of arrangements based on the size here. So if this cation, for example, was any smaller than this, then this particular arrangement with having 6 neighbors, right? We got 1, 2, 3, 4 in the plane. There's 1 up top and then 1 below. So that's 6 neighbors, or a coordination of 6. Well, if this was any smaller, then these would no longer touch this one, but they'd be touching each other. And we're saying we can't have that case. And so I'd have to change this arrangement and into a different one. And in that case, we would actually end up with a coordination 4, or forming a tetrahedron. That works better. Now, as this grows in size, that's fine. We're not violating the rule that they have to touch this one, but they can't touch each other, because as this gets bigger and bigger, then this holds. But at some point, if we get it all the way up to 0.732 relative size to the anion, okay, so the radius of the cation would be 73.2% of the anion. When we get it to that position, we can actually switch over to this structure and now increase our number of neighbors by 2. And so now we would have 8 near neighbors if we put this in the center of a cube with anions at the corners. And so it will switch over to this structure, right? Because we want to maximize the number of neighbors. Okay, so that's how we kind of reason out what structure we're going to have. All right, so now that we have that, we could go through and we could calculate, what is the size that just fits inside of a cube with the corners all touching. And if we do that exercise, we will get this answer 0.732. So that would be the minimum size. Below that, it will switch over to this structure. If we calculate that minimum size shown here, we would get 0.414. Below that, we would switch over to a tetrahedral structure, and those other cases like that are in your text. I just pulled out these 2. Okay, so that's the piece of information that we really need. All right, so the other thing we're going to need is the ionic radii, so that's table 12.3 in your text. We're going to be looking today at nickel, 0.069, and we're going to look at oxygen, 0.140. Okay. So let's take a look at a couple of different structures based on this coordination that we just set up previously. So take a look at this one over here. So the way we want to figure out the coordination is go ahead and find the center cation in this case, And then from that one, we can just simply count the number of anions that are around it that would be touching. So we've got 1, 2, 3, 4 in the plane of this one. They're all touching. And then directly above it, we have 5. Directly below it, 6. So the coordination here is 6. Okay, so this is the structure we would expect to have with a coordination of 6 based on our previous slide rules. How about this one over here? This one's a lot easier to see, right? We pick this atom in the center, and then this is going to touch each corner, which is 8. Coordination of 8. And then this structure here, if we pick this one, this is touching the corner atom, and then the 3 face atoms that are around it. This is forming a tetrahedron with that in the center here, and that's a coordination of 4. Okay. Now those structures that we just saw were all 1-to-1 ratios. Okay, so here's the coordination 8 case, and if we count, we got 1 cation, and then we've got 8 corners, each count is 1/8, and so that's also 1 anion. So this could be cesium, and these would be chloride. So that's a 1-to-1 ratio structure, and that works for cesium chloride. What if we had something like calcium fluoride? The calcium is a +2 oxidation state. The fluoride is just -1. So that means I'm going to need 2 fluorides for every calcium. Okay. So let's go ahead and count them here in this structure and see if that's the case. So now this structure is a little confusing. If you notice that this is formed up of several cubes. So here's a basic cube here in the front. Then we've got one behind, one over here, and one over here. So that's 4. And then we also have then 4 below. So this has 8 cube structures in it. Each of the cube structures have atoms in the corner. So it looks like this one for just looking at the corner atoms. And so we've taken this structure and we've repeated it 8 times here to form this overall large structure. Then we come in and we take the center atom out of 2 of the cells on top and 2 of the cells on the bottom. Okay, so in other words, only 2 of the cells out of these 4 have a center atom, and only 2 cells on the bottom have a center atom. Okay, so by doing that, we've gone from a 1-to-1 structure now to a 1-to-2 structure. So if we go through and count all of the calciums, these are all inside completely, so that's 4. Okay, again, I just want to point out this is the unit cell, this entire structure now. All right, so that's 4, they're completely in. And then if I go through and count the anions, and you can do that as an exercise, you're going to get 8. So remember, all of the corner ones count as 1/8 when you go through and count. The edges will count as 1/4. The faces will count as 1/2, sorry. And then we've got this one here in the center that's fully in, so that counts as 1. So we go through and count all of those, taking that into account, and you should get 8, or a 1-to-2 ratio. So the stoichiometry is calcium fluoride 2, right? CaF2. Okay, so if I did the ratio of these, I would end up with a coordination of 8, but then given that I've got a 1-to-2 ratio, that would tell me that this cannot be my structure, but yet this one is. It satisfies the coordination of 8, but we also have 1-to-2 between the cation and anion. So let's go ahead and look at an example. So which structure below represents nickel oxide? Okay. So we've got 4 structures here to choose from. The first one has a coordination of 4, okay, but they're all the same type of atom, so that can't be this one because this is 2 different atom types. This is actually the diamond structure. Okay, these are all carbon. This one's similar to A, still coordination 4, but now I've got 2 atom types. That's a 1-to-1 ratio. Coordination 8, 1-to-1 ratio. And here we've got a coordination of 6 in a 1-to-1 ratio. So B, C, or D can be my answer. What I need to do is just check the cation to anion ratio. And if I do that, I pulled these off of the table in the previous slide, I'm going to get 0.49 for the ratio for nickel and oxygen. And then if I go to that table in my text, I can find 0.49 is between these two values here, 414 and 732. So that means I have a coordination of 6, and I'm looking at a structure like this when I'm just considering the neighbors around my cation. All right, well, the only coordination 6 structure we had was D. So there's my cation in the middle. Then I've got 4 in the plane, 1 on top and 1 on bottom. So there they are, 4 in the plane, 1 on top, 1 on the bottom. My cation in the middle. So the answer for this then is D. This is referred to as the sodium chloride structure, rock salt structure, and that's how I determine it.